Now to solve these problems, you always want to write down Newton's second law first thing. But let me first do the coordinate system. So obviously there's a very obvious way to do the coordinate system here. Just like this. We only have to worry about one direction, so it's really just a one-dimensional problem. And the next thing is to write down Newton's second law. And Newton's second law says that the sum of the forces in each direction, this is the direction, is the mass of the object times its acceleration in that direction. Okay. So now one thing I should also make clear is that when you start drawing these arrows, actually let me write this whole thing down first. So the left-hand side, I'm just going to write up all the forces, and anything that's pointing in the positive direction, I'll make positive, and anything that's pointing against the axis, I'll make negative. And that'll include the negative g, so I don't need to put any more negative g's. I'll talk about that in a second. So on the left-hand side, I'm going to have f child plus fn minus w. And the right-hand side, I'm just going to have m, a in the y direction, because I'm only talking about the y direction. Okay, so I've already taken into account that gravity points down. Now, when I start plugging in these numbers, it tells you how much the child is pulling up with 100 newtons. It tells you're trying to find the normal force, and you know that the weight is always mass times gravity. But that already takes into account the fact that gravity points down. So don't put another negative, it's just mg. Okay? And now it's simple because you have all the other numbers, but we're not sure what the acceleration is. So the problem implicitly said he's trying to pull up, but it never says the block actually moves. So the acceleration is 0. In this case, the acceleration is 0. All in all, it's so if I solve this, I'm going to get Fn equals mg minus 100. And the mass, you're going to have to convert pounds to newtons, pounds to kilograms, so it's 60 pounds. And each pound is, each kilogram is 2.2 pounds. Don't worry about knowing these, you don't need to know them. Times g minus 100 newtons. So this is all in newtons because it's kilograms times meters per second squared. And so the solution will just be that for the force. And that's in newtons. Any questions how I did that?
Wait, so what'd you do there? 60 times?
I converted pounds to kilograms.
Okay.
And that's conversion time.
Times gravity minus 100. Okay.
Right.
Yeah.
Okay, so let's do a little trickier problem. All right, so this next problem is called the output machine. This is a good problem because it also illustrates one of the main steps on Professor Parr's recipe, which is limiting cases. We'll talk about that right now. You didn't go over this on Monday, right? You can go to class. So all this is, it's not really a machine, it's just a bunch of blocks suspended from a pulley. And the blocks may not be the same mass. And the question is, what's the acceleration of the blocks, depending on their mass? So depending on the relative masses, how many find the acceleration? So this is a good problem because it illustrates a lot of the techniques for solving it, even though it's not very hard. Now, since we have two different free bodies here, I'm going to draw a free body diagram for each one separately. So the question, let me write the question. What is the acceleration of each mass? And you can assume that the pulley, there's no energy lost in the pulley itself. The strings are pretty much massless, etc. And the only force acting on them, besides the string, is gravity. So the first thing I'm going to do is, before I draw the free body diagram, let me just draw the coordinate system. And again, it's obvious. We'll do X and Y, it's only in the Y direction. Okay, so we're just worrying about this direction, no forces in this direction. So the first mass, which I call M1, is on the left-hand side. It has two forces acting upon it, tension and weight. And if I write down Newton's second law for this, I'll have the sum of the forces equals its mass, which I have to call M1, times its acceleration. Each of these things may not be accelerating at the same rate, so I'm going to just keep them distinct for now. Now, be careful that you use your coordinate system properly. Since I called y up positive, then t has to be positive and w has to be negative. That won't always be the case, and this one it will. So I'm going to have a minus w1 equals m1 a1. The t stands for tension. Whenever you have a string, the force that it pulls on is called tension. And because this is one string, the tension on both sides will be the same. So I don't need to use two different tensions. It's going to have the same tension. Otherwise, the string will stretch. All right, so that's the first equation. The second equation is very similar. And again, tension is the same because the string is unstretched. So I'm going to write down the second law. Again, make sure you keep the masses and accelerations distinct. Not the same mass, nor is it the same acceleration. And if you look at the coordinate system, t is again pointing in a positive y, and w2 is pointing negative. So it's t minus w2. So we have a bunch of variables here that we may not be able to solve. Let me write this w1 in terms of mg. So I'm just writing that the weight equals the mass times the gravitational acceleration. We discussed that in class today. Okay. Now, there's one more piece of information that's useful here, and it's how A1 and A2 are related. And it's related to the fact that these things are tied. So if one goes up, the other is going to go down. So does anybody have an idea for an equation I can write down that relates A1 and A2? Okay, why negative?
Because the one
Okay, yeah, it's very important that you said negative. A1 equals negative A2 because if one mass goes up, the other one has to go down. So that equation typifies the fact that they're tied and they go in opposite directions. Okay, any questions how I got that? I'll tell you your name. So now if I plug this in here, I can actually find the missing quantity. I'm going to get rid of A2 and just put that in there. I'll have T minus M2G equals negative M2 A1. All I do is I plug in A2 equals negative A1. So my two equations are this and this. And we're trying to solve for A, or A1. Once we have A1, we can just find A2 as just the negative of that. So the one thing I want to get rid of is, I want to get rid of tension because there's no indication that I know what tension is. All I know is the masses of the objects and I know the gravitational acceleration. So an easy way to solve these types of equations is to either subtract them or add them. Maybe I'll just solve this one for t. So if I solve this one for t, I'm going to have t equals m1 a1 plus m1g. And I'll plug it in there, which will give me, if I plug in this quantity for t, it's m1 a1 plus m1g. And then the remainder is minus m2g. And then the right hand side. And now it's just algebra to solve for a1. You can check that out.
Do you know the G's?
Times G thing. Okay. It seems like a very simple problem, but the answer is actually, I mean, it's not trivial. What the actual acceleration is. Yeah, sure.
I was just wondering, who did that? Are negative but tensions equal each other?
No, I solved this first one for the function, and I plugged it in here. So I replaced this t with this.
Oh, right.
I just solved this two equation. Okay, so what we want to do now is actually talk about the limiting cases. In other words, does this make sense if certain things are equal or certain things are not bigger than others? For example, if I had the same masses, what would the acceleration be? 0, right? Because they would make down. Does that make sense in the equation? It does, because m2 minus m1 is their numerator. If they're the same, that would just be 0. So it makes sense. Let me write this up here. Limiting cases. That makes sense. What about if mass 2 was really, really heavy and mass 1 was really, really light? In other words, mass 2 is much bigger than mass 1. If I had like this huge block attached to this tiny block, what would the acceleration be going down? It pretty much be like a drop, so it'll be like g. It should be about g. Let's make sure that makes sense. When m2 is much bigger than m1, then in this formula here, the numerator is going to be pretty much as m2 because that won't matter, and the denominator will just be m2 because that won't matter. So I'm just going to have 1 over 1 times g, or m2 over m2 times g equals just g. Does that make sense?
So pretty much like if you take the limit as m2 goes to infinity and m1 goes to 0,
Right.
it'd be g.
Yeah. And you don't even have to take m1 to 0. M1 is fine as long as m2 goes to infinity.
Okay.
Yeah. For testing situations, you know, like sometimes you may not be able to figure out a problem because you may be running out of time or you're stumped or whatever. If you have a problem that has a bunch of choices like this, and you can rule out some of them, this is a good way to rule out something. You can always check what do you expect to happen when something is really big or when some things are equal. And if you can rule out this because it makes no physical sense, then you can cross it out and increase your chances of just guessing right, which is always useful. Because this test is all multiple choice. This test is all multiple choice. And probably every test you'll take in your lifetime. So it's a useful testing scenario. I'll do one more problem kind of like this, and I'm going to do the elevator problem from the homework section. Actually, no, let me do number 12 on the homework. That's not too hard. Number 12 on the homework is page 111. It's the one with the grade blocks being pulled.
So does that formula you just got for acceleration only for like a system like that where they're pulling in opposite directions?
Yes.
Okay.
We'll do one that's similar to this, but not the same. We'll get different formulas. All right, so the problem says there's 3 blocks being pulled. And it's frictionless. We'll talk about friction when we move on, but for now it's frictionless. So let's imagine that 3 blocks being pulled on ice by a figure skater, right, or something. And he's pulling these things. And the tension here is given, T3 is 65. And these are unknown, T2, T1. I'm going to use the numbers in the book. So the number in the whole of that change, I'm going to use the numbers in the book just for illustration. So M1 is 12, M2, 24, and M3 is 21. So there's 3 parts to this problem. The first one says calculate the system's acceleration. This problem is a really good illustration of how things can be very difficult if you just try to rush through it and don't use a few body diagrams. So I'll do it step by step. So the first thing I'm going to do on a coordinate system, there's an x direction where it's being pulled in a y direction, which is where gravity acts. it's really asking what's happening in this direction, but I want to write down the equations for both just to be complete. So we need to do one for each of these masses. Let me start with mass 1 and do mass 2. Okay, so this mass has a couple of forces on it. It has its weight pulling it down, and it has a little force keeping it from falling into the ground. And it also has a tension T1 pulling it to the right. And that's it. Now I can solve the y equations. The y equations won't give me much information. So let me just do the x equations. So what's happening in the x direction? I'm going to call this A1. Okay, so it's two subscripts. The 1 refers to the fact that it's block 1, and x refers to the fact that it's the next one. Now the forces in the x direction are just T1. So all I have is T1 equals M A1x. And you notice that T1 points to the positive x direction, so I'm making it positive, according to my code system. Okay, so that's that block. It's pretty straightforward. And if I do the y equations, again, we're not asked to find this, so it's not really that critical. The forces in this direction, well, Fn is pointing in the positive y, and then weight 1 is pointing in the negative y. And it's not moving up or down because it's stationary in the y direction, so the right-hand side is 0. So all that gives us is that the weight equals normal force. Not really that important. But this equation is in your book somewhere, and it only applies to a situation like this. I did a problem a minute ago with a child pulling over that thing, and the weight did not move because there was a third component pulling it. So this is not always true. Really, we're going to be using this one. This one's important. Now, we'll do the same thing for the second body. The second body will have different forces on it. I'm just going to do on the x forces. I'll just worry about the x forces. And this coordinate system will be the same, x, y. So if I look at the x direction, the forces in the x direction are T2 positive and T1 negative. So I get this. And then that equals M2A2 in the x direction. And then likewise for the third block. It's the exact same thing. Except for T3 and T2. So you get T3 minus T2 equals M3A3x. So we have three equations that may be useful. The problem right now is that we have three different accelerations, but there's a relationship between them. In this case, they're all the same, because if I pull one block to the right, they're all going to go to the right, the exact same result. Okay, so A1x equals A2x equals A3x. That's like an added condition. And I'll call that A. So do you guys know what this 3 equal sign is? That means I'm defining something. That means I'm just going to call it that. That may come up later in your education. So I'm going to call this A. Okay? So my three equations, therefore, are going to be these. So I have T1 equals M1A. I have T2 minus T1 equals M2A. And I have T3 minus T2 equals M3A. And the question is asking, well, what is A? And I have a bunch of equations, so I can get rid of a bunch of variables. And the easiest way to solve this is by adding up all the equations on either side. So if I add up on the left side, I'm going to get this plus this minus that plus this minus that. So I get T1 plus T2 minus T1 plus T3 minus T2. And this has to equal whatever on the right hand side is added up. Okay. On the left hand side, it's simple because these start to cancel out. That's why I do this. So all I end up with is T3 equals the sum of the masses times the sum. So the acceleration is just simply the total force acting on the whole system divided by the total mass. You may be thinking to yourself, this seems like a really long-winded way to do something, well, all I could have done was pretend it was one big block. And I would have got the same thing. If you just pretended it was one big block, you would have had like this kind of thing. The T3 pulling in, and you would just get T3 equals the sum of the masses times the square root of T. Yeah, that's right, because they're all added together. But that wouldn't tell you how T1 and T2 are related to T3. So you can get the acceleration, but to go further, we have to actually use this process. So let's go further and find out what T1 and T3 are.